Okay, so starting with number 12 here, we're given a force, and it follows this function here, and we're supposed to find the average rate of change of the electrostatic force F on a given interval in millimeters, and F is newtons. So to find the average rate of change, we have our formula where we just have F of 4 minus F of 2 over 4 minus 2. It's the exact same as like the slope formula. So from here, all that we need to do is just start plugging numbers in and working it out. So F of 4 is going to be 2 over 4 squared. And then F of 2, we'll have minus 2 over 2 squared over 4 minus 2 is just 2. So going from here, we're going to have 2 over 16 minus 2 over 4, which is just going to be 1/2 over 2. And again, 2 over 16 we can write as 1/8 minus 1/2, all divided by 2. And so to add or subtract fractions, we need common denominators, which means that we can go ahead and write this 1/2 as 4/8 over 2. So now 1/8 minus 4/8 is going to be negative 3/8, and we're going to divide this by 2. So if we divide this by 2, we get negative 3 over 16. So our average rate of change is negative 3 over 16, and we need to include units. So if force is newtons and distance is millimeters, we will have newtons over millimeter. So that's what our final units are going to be. It's going to be newtons per millimeter. Okay, so for number 13, starting with part A, we first calculate F1 and F2 for the function, and then we're going to calculate some average rates of change. So for F1, all we do is plug in 1 wherever we see x. So F1 equals 5/2, 1 plus 3 squared. And so this should come out to be 40. And then next we do the exact same thing with 2. So we plug in 2 wherever we see x. 2 plus 3 squared. And this should come out to be 62.5. So now we need to calculate the average rate of change over these intervals. So again, like on number 12, we use the same formula where we're going to have F of 2 minus F of 1 over 2 minus 1. So F of 2 we said was 62.5 minus F of 1 was 40 over 2 minus 1, which is just 1. So that gets us 22.5. Okay, and on part C, we're going from 1 to 1.5, and notice it gives us these numbers here. So we're going to have F of 1.5 minus F of 1 over 1.5 minus 1. So this is going to be equal to 50.625 minus 40 all over 0.5. So if we go ahead and work this out, we should go ahead and get 21.25. And then for part D, we go from 1 to 1.1. That's these numbers here. So F of 1.1 minus F of 1 over 1.1 minus 1. So that's going to be 42.025 minus 40 over 0.1. And that should get us 20.25. And then for part E, we're going even closer. And we're going to have F of 1.01 minus F of 1 over 1.01 minus 1. So we have a really small interval. And our answer is going to be 40.20025 minus 40 all over 0.01. And if we enter this into our calculator, we should get 20.025. So looking at part F here, says what might be a good approximation for the instantaneous rate of change of x equals 1. So if you look, we started at going from 1 to 2, then 1 to 1.5, and 1 to 1.1, and so on. We made this interval smaller and smaller until we're getting really, really close to 1. So the idea is that as we go smaller and smaller numbers, we can get closer to finding the instantaneous rate of change for x equals 1. So if we look, we started at 22.5 and we kept getting smaller and smaller until we wound up with a number really, really close to 20. So we can go ahead and assume that a good approximation for our instantaneous rate of change at x equals 1 is just going to be 20. Okay, and for this last one, 14 here, fill in the blank. If f of a equals f of b, the average rate of change of f on the interval a to b is, okay, so if we have, remember, f of b, minus f of a for b minus a. So if f of a equals f of b, then f of b minus f of a is just going to be 0. So we should expect our average rate of change for that interval to be 0. Okay, so number 15 now, and we're going to start with part A here. So for part A, we're finding f of b. So f of b is going to be the y value right here, which is just corresponds to r, right? So f of b just equals r. Now moving on to the next one, we're finding f of x equals r. So that's kind of working in reverse. We're going to go through here, see, okay, equals that, and it equals that. So we should expect this to have our x equal b or d, okay? And then for c, we're finding, solve for when f of x equals 0. Well, if we look here, this is where 0 is at. Our graph of f never goes down to there, which means that we have no solution. No solution. Okay, and for part D, find intervals where f is increasing. So if we look at our graph here, we should go from here on up. We start increasing, right? So anything that's greater than c. So what we're going to do is we're going to do c to infinity. And I notice I put parentheses at c because at z we don't really, or excuse me, at c, because we don't really know that we're increasing right at c. So that's why I use parentheses. Okay. And then for e is the average rate of change of the interval from c to d, positive, negative, or 0. So let's kind of clean this up. Okay, so our average rate of change from this point here to this point here. So if we look, we have a positive slope. A positive slope indicates that our average rate of change is positive. So this here is positive. So this next one is f of d minus f of b over d minus b, positive, negative, or 0. So we are looking at f of d. So f of d is here, and f of b is here. So if we look from these 2 points here, notice how we get a horizontal line. So because our slope is horizontal, that means that this here, this is all going to be, this is our average rate of change from D to B, is going to be 0, because we're not changing between those 2 points. So this should be 0. Okay, so moving on to 16. If g is a decreasing function, which of the following is the largest? Explain. So if we kind of just look at what g might look like. G could be something kind of like this, right? Just a decreasing function. And if our function is always decreasing, the further left we go, the larger values we get. So we should expect that whenever we plug in a smaller x value, we should get a larger g of x value. So if we look which one of these is the smallest, we have -8, -1, 0, 3, and 10. So because -8 is the furthest left, we can go ahead and expect this to have the largest value for g of -8. Okay, number 17, final intervals for which the function is either increasing or decreasing. Use interval notation. Okay, so let's start with just increasing. So if we look here, you can see that from -3 to this point here, we're going upwards, which means that we're increasing. So we should expect this to be -3 to, was that -1? Yeah. Okay, and then for decreasing, we can see that we're going from -infinity all the way to -3. Our function is decreasing downwards, right? And then the same thing from here, from -1 to infinity. So the way that we're going to write that is we're going to use parentheses, -infinity to -3, and then union from -1 to +infinity. Okay, 18, sketch a graph with a domain from -4 to 8 that has a negative rate of change from -4 to 2 and a positive rate of change from 2 to 8. So first thing that I'm going to do is just kind of mark out my boundaries here. So my graph should be inside of these two lines here. And then if we have a negative rate of change from -4 to 2, that means we're going to be going downwards, right? So maybe something like that. And then a positive rate of change from 2 to 8. So that means that we're going to be going upwards or something like that. And notice that I'm going to put 2 dots here. So that way that shows that our domain is inclusive of -4 and 8. Okay, so for number 19, the graph of the function g with domain -2 to 7 is shown. Find each of the following using interval notation. So where are we increasing? So looks like we're increasing from here to here. Then we're also increasing from here to here. So how do we write that? Using interval notation, we're going to have parentheses, -2 to -1, and then union 4 to 7. Okay, and next we're looking at our decreasing intervals. Well, we're decreasing from here to here. So that is -1 to 4. So we're also going to use parentheses, -1 to 4. Okay, and then finding our local maximum. So if we follow our graph along, we can see that the highest point is at this spot right here, and the lowest point is this right here for our locals. And all that local means is just that it's the smallest or largest in its region, sort of. So this one here is the local minimum, and this one here is the local maximum. But if we look, this point here isn't the largest that our function gets because we're larger over here. But this is what we call our local max because everything right next to it is smaller. And typically what's common of that is you would see that your slope goes from increasing to decreasing. That's typically what happens. So our local maximum is that x is at 4.3 at x equals -1. The local minimum is -8.2 at x equals 4. And then the absolute maximum is going to be this up here, and our absolute minimum is right there. And that's just like the overall, looking at everything. So the absolute max is 10.7 at x equals 7, and -8.2 at x equals 4. Okay, number 20, assume the graph has domain -infinity to +infinity, and all relevant features are shown. Using interval notation, estimate the entire x intervals where the graph is increasing and concave down. So quick recap, if we're concave up, we should be getting something kind of like this. It looks like a smiley face. So this is concave up. And if we're concave down, it's something more like a frowny face. where this comes from is really, it's whether or not our slope is increasing or decreasing. So if we're concave up, our slope is increasing. And if we're concave down, our slope is decreasing. Okay, so looking at this, increasing and concave down. So if we're increasing and concave down, that's kind of like this first portion here that I'm highlighting right here. Because our slope is still positive, but we're concave down, which means our slope is decreasing. So if we look at our graph, it looks like that's happening from right around here to here. So where we're increasing, but we're also concave down. So I'm going to say that this is from -1 to 0. And the reason why I didn't include this little section before it is because this still kind of looks like the slope is increasing here. And that happens a lot in these sort of quadratic functions where you get something where the slope is increasing and then the slope starts to decrease again. And what you call it is actually an inflection point. So moving on to where we're decreasing and concave up. So if we're decreasing and concave up, that's going to be something like this portion here. So we should expect a negative slope, but it still should be looking like our slope is going to be kind of moving upwards. So that looks like all of this section here. So our slope is negative, but it's starting to increase or kind of get into like this sort of shape right here. And that is the only section that happens here. So we're going to say that goes from -infinity to -2. Okay, and for part B here, find the local maximum and or minimum. So that's just going to be this point here, this point here. We can see that even though, again, we're larger up here than we are right here, it's called a local maximum because our slope is increasing and then it starts to decrease. So we kind of get this sort of shape here. And this point here is what we call our local maximum because it's the largest of anything that's near it. So this here is our local max. This here is our local minimum. And the minimum is just the smallest value. So our maximum appears to be -3, and that's at x equals 0. And then the minimum is, let's see, oops, is that -7 at x equals -2. Okay, and what is the approximate x value of the inflection point? So that kind of goes back to what I was mentioning earlier, where the inflection point is where our slope goes from increasing to decreasing or decreasing to increasing. And that's our slope, not our graph. So earlier I'd mentioned this point right here at x equals -1. That's because if we look at this, we change concavity right here. So we go from our slope is increasing, then our slope starts to decrease here. So our concavity changed, which means that that's an inflection point. And it could have been the opposite, where our slope was decreasing and then it began to increase. That would also be an inflection point. But really what we want is a change in concavity. So this happens at x equals -1. Okay, so number 21, consider a function f that has a domain of all real numbers. Sketch a possible graph of f, or a function g with the following properties. Okay, I think that's just a typo. So the rate of change of f is negative from -infinity to 3 and from 5 to infinity. So I'm just going to kind of mark these 2 points here. And then we also know that our rate of change is positive from 3 to 5, and that the graph of g is concave up from -infinity to 4, and then concave down from 4 to infinity. So from -infinity to 3, we're decreasing, but we're also concave up. So we get something kind of like this here, right here. And then from 3 to 4, we start increasing, but we're still concave up. So we should expect this shape here from -infinity to 4. So I'm going to kind of roughly sketch something out. So maybe we go something like this, and we start increasing here, kind of like that. okay? And then the next step is that we keep increasing, but we're now concave down from 4 to infinity, and also that we begin to decrease from 5 to infinity. So what that might look like is something kind of like this here. So we can see that we're decreasing in concave up, then we're increasing in concave up, then increasing concave down, then decreasing concave down. So that should follow what we have here. At what x values does a local maximum or local minimum occur? So local maximum, if we look at our graph, it occurs right here, which is x equals 5. Then the local minimum is right here. And again, those are just where our slope changes from negative to positive or positive to negative. So those 2 points, we get a max for x equals 5 and a min at x equals 3. So this next one, for what x value the inflection point occurs. So the inflection point again is whenever we change concavity. So if we look, notice here, we say that we go from concave up to concave down, which means that our concavity changed between, at that point, 4. So our inflection point is going to be x equals 4.